Great, so let's jump in and do some analyses of the Factorial ANOVA in R. So I've already installed and loaded up some packages that we're going to need later on so that we don't need to run them live. And I've also loaded up that clinical trial data that we've talked about before. So some of these data will look pretty familiar. So far, we've only looked at one of the variables at a time. So to remind you, let's see what this looks like. So we have data for the drug and we have data for the therapy. And so for this, there's actually 6 cells because it is a 2x3. So there's either no therapy or there's CBT, cognitive behavioral therapy, as the experimental condition. And for the drugs, there is placebo, anxiety-free, and joyzepam, the 3 different drugs that you could take. So basically, placebo is the control condition, and there's 2 experimental conditions. So what you're seeing here is that we do have a balanced design. So the assumption is met to run a Factorial ANOVA like we usually would for this data set here. So if this was not all exactly the same, that would not be met. All right, so just depending on the specific hypotheses, we're going to be interested in comparing different sets of means. So maybe we are just interested in comparing each of the sets of means like so. So you have all 6 of these listed, and we have for each of those cells, basically a mean for each of them. We have people in the placebo and no therapy condition, and the placebo and CBT condition, et cetera, et cetera. So you might remember from very early in the semester, I said, oh, we can eyeball these, but maybe we want to compare these to see what differences there are. So another way that you could break this up is like so. So maybe you don't actually want to compare all 6 of those conditions. Maybe you want to just compare the 3 separate drug conditions. Or in contrast, maybe you want to have it split up this way so that you have whether they're in therapy or not, and then you get this set of means. So when you are running a Factorial ANOVA, you're actually able to work with all of this data and look at these all at the same time. So you'll be able to use the fact that there's 6 separate means. If it's split based on the drug, it can be split 3 ways. And if it's split by therapy, it can be split 2 ways. So there's a lot of different information that we can work with. And of course, we can compare that all to the grand mean, which is all 6 of the groups combined, or all 3 or all 2, depending on how you split it up before. So when we're doing the analysis, we'll be looking at all of that information at the same time, and then we'll also be doing some interactions as well. So as a review, this is what it looked like when we were running a one-way ANOVA. So you remember we run the AOV function. We specify the dependent variable, which is mood gain, and then we specify the predictor variable, which here was drug, and it's coming from the data frame clinical trial. So if you run this and we take a look at it, let's just again take a glance to see what that looked like. So you see that you get the degree of freedom, sum of squares, the mean square, which is divided by degrees of freedom. Then you divide that out to get the S-statistic, and you get a p-value for that. So some of this is going to look familiar when you run a Factorial ANOVA. So for this one, you also use the AOV function, analysis of variance. So again, that's very similar. Again, you specify the dependent variable first, you have the tilde symbol, you have whatever you want your first variable to be. In this case, you're just keeping a drug, and then you have a plus sign and the second variable that you're including. And if you wanted to make it increasingly complicated, you could keep on adding plus, 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 but that gets, like I was saying in the last video, extremely complicated. So we won't get into that in this class, but if you wanted to, you could. And again, we're specifying the data frame. So in practice, this is set up very similarly. The syntax is based on actually the same function. So let's create that variable, model2, that's saving all the information as a list. And then let's run the summary to see what comes out here. So what you see is that we have summary statistics for the drug and for the therapy effect. So the drug has 2 degrees of freedom, just like this one up here. And this is actually telling you the same thing as in the one-way ANOVA. So again, it wouldn't really be much value to have this if we're just looking at these two at the same time. You could just run the drug as a one-way ANOVA, therapy as a one-way ANOVA, not as much gained. So then you see the therapy effect here is here as well. So in this case, they were both significant, and then there's some variance left over. So let's look at some means that are being calculated to get a little more in depth into the factorial ANOVA. So here I'm creating drug means, and I am aggregating across different values here. And so I'm going to get these 3 means for the 3 drug conditions, the therapy conditions, and also the grad mean. So rather than, looking at those individually, we are now calculating this out individually. You can also then calculate out the sum of squares manually. So let's go through that. Again, the sum of squares is going to be very familiar to what we were doing with the one-way ANOVA. In this case, we are going to get sum of squares for the drug condition. We're going to get sum of squares for the therapy condition, and we're going to get sum of squares total. So let's take a look at what we got that's coming out there. So you see this is like 3.4533. That's just rounded up 0.46, same here. And then the sum of squares total will be when you add up all of that information. And then, of course, similarly, the residual is everything that is left over here. So here we are able to break this down into how much of the variance is associated with therapy, how much is associated with the drug, and how much ends up being left over at the end. So there's not too much variance left over when it's all said and done. Like I said, not too exciting yet, but again, the big value here is that we could test those interactions. So let's first of all plot this out, and I'm going to make myself a little bit of space here so that we can actually see the plots come up. So here I'm going to be running a line plot with confidence intervals, and it's going to be splitting by drug and looking at mood gain. And it's also going to be splitting by therapy. The confidence interval is around the mean. So this is going to plot some confidence intervals. And then here we're specifying the x variable and the y variable. So let's run this first, and we'll take a look at what it's showing us here. So this is just a visual plot of all those means with a 95% confidence interval. So here you can see that what it looks like is that the cognitive behavioral therapy overall has higher means. No therapy is overall a little bit lower. The biggest difference just at a glance seems to be that for anxiety-free, there's a bigger difference between cognitive behavioral therapy and no therapy, whereas for joyzepam, it doesn't seem to matter too much. You can also look at that the other way, and you could also focus more so on which of the 3 drugs, and it seems like joyzepam is the highest as compared to the other ones. So let's actually run this interaction in R. So if you want more than just the main effects, you actually have to specify this a little bit differently. And again, in most situations, you are going to want to know the interaction information. So this is probably more what it's going to look like when you do your own analyses. So there's different ways of specifying this that I'll go through. So I'll first run this one and walk through how this works. So again, you're using the same AOV function, specifying the dependent variable is mood gain, and then you have drug and therapy. So those are both included in that model, because remember now at this point, we're getting complicated enough that we're able to set up our model of what we think matters. Here we're also specifying drug colon therapy. There is no space in between those two. If you put a space, you'd get an error there. Remember specifying that this comes from clinical trial. And so what this is going to do is that this gives you the information about the interaction between drug and therapy. So we'll run this and look at it just relatively quickly, just to make sure that that worked. And we can also run it a quicker way. So if you want to list variables that are interacting with each other, it will by default also run everything for the lower level effects. So if you ever hear lower level effects or lower level whatever when talking about a model, what that typically means is that you have something complicated like an interaction, and you also have more basic stuff that's going into it. So this is saying drug times therapy. And so the AOV function knows that if you're doing this times thing, that means that you also want to keep in the lower level effects. So this is just a different way that you can write it. If you had a whole bunch of variables, it might be easier to do drug times therapy times something rather than having to remember, oh, I have to type out all of these iterations. So if you get into a longer form, this second version is easier to write. So let's go ahead and run this and take a look. All right, so here you're seeing that there's some of the same information here for drug and for therapy. So this will look pretty familiar to what we were looking at before. 3.453 sum of squares, 0.467 sum of squares. And so there was some stuff left over. And now this is variance that is associated with the interaction between drug and therapy, that the effect of drug depends on therapy, or if you're thinking about it the other way around, the effect of therapy depends on drug, and you're able to look at this interaction. So here we are getting a sum of squares, which is basically variance associated with these 6 means that's not already accounted for by the mean between the 3 groups for drug and the 2 groups for therapy. So there will be that residual left over, and the interaction is using up some of the sum of squares from that residual. And then you'll have the degrees of freedom, which is multiplying these degrees of freedom, essentially. And you get an F statistic for that as well. So what we're seeing here is that there is not a significant interaction pattern. So unfortunately, that hypothesis didn't work out in this case, which in reality happens more often than you actually do find a significant effect. So essentially what that's leading us to conclude is that the effect of drug does not depend on whether or not the person was in therapy. And similarly, the effect of therapy does not depend on whether or not they had the drug. So it seems like the joyzepam helps just by itself. It seems like cognitive behavioral therapy helps just by itself. But it doesn't seem to be, based on these analyses, that a specific combination has especially strong effects. So if we had an interaction, that's what we would conclude. And then we'd be looking at the pattern and seeing, okay, where is the difference really lying? So again, if you're just looking at something visually, it can look like maybe that was different, but essentially this is telling us that there's no statistical significance there. So basically we are retaining the null hypothesis that the effect of one variable does not depend on the level of the other variable. Right, so we do also use eta squared when we get into factorial ANOVAs. Let's go ahead and run that. So for model 2, which is just listing both of those variables, you see that we get eta squared and for drug and for therapy. So again, that's going to be pretty basic information. If we run the eta squared for the model 3, now we are going to get eta squared values for both the drug, the therapy, and then for the interaction between drug and therapy. So basically, this is telling us that about 6% of the variance in mood gain is accounted for by the interaction, although that is not statistically significant. So when you start putting a lot of things in the model, there's a bigger difference between the eta squared and the partial eta squared. So the eta squared is the total variance. And the partial eta squared is the amount of variance that's accounted for that isn't overlapping with those other variables. So basically, for the drug therapy, it is comparing how much variance was accounted for as a proportion of the total residual. So it's basically, if you add these two together, it was like 0.924 or something like that. You divide 0.271 by 0.924 and you get this. So there are differences in terms of who reports eta squared and partial eta squared. As the author suggested, that's probably in part because a partial eta squared is larger, and so it looks a little bit better, but it can be a little bit confusing. So I'd usually at least give both pieces of information if you're asked to do partial eta squared anyways, because it can be potentially misunderstood. You could look at the interaction and say, well, the interaction is accounting for 29% of the variance, but really it's only accounting for 6% of the total variance. It's just that because the main effects ate up about 80% of the variance, there wasn't that much left to explain. So you can explain a good chunk of it, even if what you are explaining with the interaction isn't even statistically significant. So that's the difference there. And you see sometimes in papers that they only report the partial eta squared, which in practice they shouldn't. You can always figure that out yourself by just looking at the sum of squares in an ANOVA table. So that's something that you can check if you think, oh, that sounds unrealistic, that's something accounted for that much variance. Sometimes it's because they're not giving you all the information. So that's a nice hint for trying to pick out critical things that are wrong in papers. Because that's something that people can often misunderstand. Even other professors can sometimes misunderstand that. So this is an example of a saturated model. So what saturated means with a model is that everything that you could include in the model is in there. So we have the one variable, we have the other variable, and we have the interaction. There's no other combination we can do with these variables. And so when you're running with a saturated model, which I generally suggest that you do, you don't have to worry much about any of the other information. However, there might be circumstances where you only are running things for part of the model. For some reason, you might only be interested in the size of the interaction effect, not accounting for the other variables. That's probably going to be pretty uncommon, but that might be the case. So let's pull up the effects package here. And so we have this effect function here, and how this is written out here is that the first thing is the term, and here we're saying the interaction between drug and therapy, and what it's coming from is from that model 3. So it's only taking that interaction. So if we ran that and we didn't include the other information, we just use the information from the interaction term, we would be able to get the means from those individual groups in this output. So that's something that might be valuable for you to do if you are running unsaturated models. That's not something that I have done, but in some areas of research, they might calculate it that way. So this is kind of why I'm walking you through this. But what happens is that then it's estimating the means if your tests don't include those mean comparisons in the ANOVA. And so you're getting a 95% confidence interval. You're getting the estimation, the lower bound, and the upper bound, essentially. So let's say that we tested it with an unsaturated model. In this case, what you're going to get is that now these values will be slightly different than the actual values that you got. And if you want, you can go ahead and compare all those means to what we had before. So again, something that you might not all use, but something that might come up in future research. Right. So one thing that we also want to take into account is the assumptions. So some of these are going to work pretty similarly to in the earlier ANOVA stuff. So I won't dwell on this in too much detail. So one of the things that you want to look at is whether the assumption of equal variance is met. So you can run the Levine's test. So let's pull up the CAR package, which is that applied regression package. So with this, we can run the Levine's test for model 2. You can also do Levine test and put in the information directly as well. So if you do this, you're going to get this error because the Levine test can only be done if you specify a saturated model. So if you do the unsaturated model, it basically will get confused. So even if you are not interested in all of the interactions for some reason, you do still have to specify the saturated model, and then you'll get the Levine's test. And here, you see that the Levine's test is not significant, which means that the homogeneity of variance assumption is met. We don't have to worry about that. So you can also test the normality of the residuals for the model, like in the one-way ANOVA. So let's say we want to run this. This is, again, going to look pretty similar, so I'll just go through it a little quickly. If you run this, histogram suggests that there's maybe a little bit of non-normality here. This is not looking like a normal distribution. If you look at the QQ plots, you can see that hopefully we would have this line going here. So it seems that maybe there is a violation of normality for the distribution of the residuals. And let's say we run the test here, we can then see, okay, it looks like it's maybe a little bit of non-normality, but the Shapiro-Wilks test is not statistically significant. So that suggests that it's not extreme enough that we really need to worry about it at this point. So again, all that should be pretty familiar from the ANOVAs. One thing that I will say about testing the assumptions about the residuals is that there will be different residuals depending on how you set up the model. So it's the residuals of the specific model that you test. So if you have like different versions of models that you're running with or without the interaction, there is more of the residuals left over for model 2 because there was not the interaction term. If you ran it for model 3, there will be different residuals. And it could potentially be the case that there is not a violation of assumption of normality for the residuals for model 2, but there could be for model 3, even though you're using the same data, because the residual variable is now different. So that would be something that I would just keep an eye on, is that anytime that you set up a model differently, you then have to check that assumption, how to do with the residuals again. So You can, similar to what we were talking about before, compare model fit for nested ANOVAs. That is adding in predictors, adding in regressions. So that, again, is going to work pretty similarly. And so if you pull this up here, you can compare this first model that only had drug in it to one in which there is drug and therapy and interaction between drug and therapy. And so this is statistically significant, meaning that adding in therapy and its interaction accounts for more variance than just having drug as a predictor. You could do that, again, anytime that you have a more basic model and you're adding stuff in. So this is just showing you how you would run that if you wanted to do this manually. So I'm leaving this in here for your own example. But again, this is going to be very similar to what we were doing with the regular ANOVAs. So I think for most of you would get that, but feel free to check that out if you want to. The next thing I want to talk about is a little bit more about how that ANOVA is based on linear regression, and talk a little bit more about the similarities between that type of data. So for the rest of the stuff, I'll come back in the next video and wrap up this section to finish up talking about factorial ANOVAs. So I'll see you there.